In this video, I'll show you 5 Python decorators that you need to know. But first, let's understand what a decorator is. Now, a decorator is really just a function that modifies another function. There's a bunch of built-in decorators in Python, and we can also write our own. Now, I want to look at an example of writing a custom decorator so we can understand what's actually happening behind the scenes when we use the built-in ones in Python. So what we see here with the timer function is a decorator. Notice that what it actually does is return another function. Now, we'll dive into that syntax in a second, but let's look at how we use this. What we do is we write the @ symbol, then the name of the function, in this case it's timer, and we decorate a function with it. We put it on top of this function. Now, you may have seen this in other modules like Flask or Django, where we actually have these decorators to define different routes, and we use them all over Python. Really, behind the scenes, they're functions that look something like this, and what they do is take a function as their first argument and then return a new function that will replace this function. Seems a little bit strange, but let's look at some equivalent syntax. So rather than using the decorator syntax here, which is the @ symbol, what we can actually do is write the following line. We can say the example function is equal to the timer function, and then we can pass the example function to it. When we do this, this is effectively the exact same as simply writing the decorator above the function. I know, seems a little bit strange, but that's all it's doing. It's simply taking this function right here, passing it to this decorator, and then replacing the function definition with whatever's returned from the decorator. So as you can see, what the decorator really does is modify a function and typically add some behavior around it. In this case, what the timer decorator will do is simply time how long it takes for a function to run. So let's have a quick look at actually executing this code, and then we'll dive into the syntax and understand how we write a custom decorator. So let's start by running the code without decorating this function. When I do that, you see that we get the sum is, and then this huge number. Now let's clear that and let's add our decorator. So we'll say at timer. Now, when we run the code, you'll notice that it tells us how long it took the function to run, and then it tells us the sum. Now let's clear that and let's use that new syntax that I just showed you. So rather than decorating the function, we will say that the example function is equal to the timer, and then we'll call the example function. Since this returns a new function, we're just saying this function is now equal to a different one. And now when I call this, we'll get the exact same thing. So that's what happens when we use a decorator. Now let's dive into this syntax. So let's start with the first function here, which is timer. Now notice that our decorator functions are always going to accept at least one argument or have one parameter, which is the function that they're modifying. So in this case, we take in func, and that means any function that we actually decorate with this decorator will be passed as the first argument. This allows us to use this decorator for any type of function that we want. Then what we do is we write some kind of wrapper function inside of this function. It might look like strange syntax, but it's totally valid to define functions inside of other functions in Python. This is known as an inner function, and there's some more complexities, but we don't need to get into that. Now within the wrapper function, what we accept here is always star args and star quarks. Now really what we're telling the function here is that we don't know how many arguments are going to be passed to it, because this timer function could be used to decorate any function. So we're going to accept any number of positional arguments and any number of keyword arguments. If you've never seen this syntax before, that's all it means, except any number of positional arguments and any number of keyword arguments. Then what we do is we start a timer. So this is our custom functionality that we're adding or decorating the function with. So we start the timer by getting the start time. We then actually call the function. So we say the result is equal to the original function, which was right here. And then we pass to it whatever the arguments and the keyword arguments were that were passed to this wrapper function. We then figure out what the end time is, and then we print how much time it took to run this function, and then we return the result. Now, the important thing is that we always want to be calling the function that we decorated. We want to store whatever the result was, and we want to return that result. This way, the decorated function will always work exactly the same as if it wasn't decorated, except we've added some additional functionality, right? So in this case, we're just starting a timer and seeing how long it took the function to run. There's all kinds of advanced decorators and more use cases that we can look at, but that's the basics of a decorator. You write a function, it accepts some function as the first argument. It can accept other arguments, but in this case, we just accept one. We have some wrapper function defined inside of it. This wrapper function always accepts any number of positional and keyword arguments, so it's dynamic and can work for any function. We add some additional functionality, call the original function, and then return whatever that result is. Now, when I go and I use my decorator on top of any type of function, it will work and it will allow me to add that timer functionality to it. Now, if you want an entire video tutorial just showing you how to write custom decorators, I'll link one on the screen. But for now, let's look at 5 built-in Python decorators that you need to know about. But first, another thing that you need to know about is that even during this really tough job market, the program that I run with Course Careers is still helping students land software development jobs. We had a student complete the program in 39 days, and in under a month later, he landed a junior developer position making $70K per year. If you want to learn more about how that works, I have a free introduction course that you can check out from the link below. There's a ton of value in there, and even if you don't purchase the course, it really breaks down what you need to do in 2024 and beyond to qualify for these junior developer positions, because just being honest with you guys, it is harder now than it was a few years ago, but it's possible if you have the right guidance and you know the path you need to follow. Anyways, check it out from the link below. So the first decorator we need to look at is known as property. Now this is used for various methods inside of a class, and the idea here is that we can treat a method as if it was an attribute, and we can gate the access to a specific field or attribute in Python. Now you may not know this, but in Python we don't have access modifiers like private, public, and protected. If you don't know what those are, don't worry, but in other programming languages, we have a way to determine whether or not an attribute can be accessed from outside of the class. In Python, we don't have that, so what we do as a convention is we add a leading underscore before any of the attributes that we define inside of our instance that we don't want to be accessed outside of the class. Whenever you see something that starts with an underscore, that indicates that it should be treated as private, and that means that I shouldn't come here and write something like c._radius equals 10. Even though I can do that, we're denoting to the user of this class that we shouldn't do that, and really this should be a private attribute. Now the reason that's important is that we typically use property in combination with a private attribute so that we can actually control the access of the attribute and whether you can set it, delete it, etc. So what we've done here is we've written a method called radius. All this does is return the value of the private attribute radius, but we've denoted this as a property. Now when we do that, that actually allows us to access the name of this method without calling the method from our circle object. So in this case, I can say c.radius, and that's actually going to call this radius method and return whatever's inside of it. Now just to show that to you, if I say print called me here, and I run this, you'll see that it says called me, and then we get 5. 10, then it says called me, and we get 10. So the idea is we're going to go through this radius method every time we try to access the radius property. Now, as well as a getter, which is what this is known as, we also have the ability to add a setter. Now, a setter is what will be used when we actually want to change the value of the attribute. In this case, we always use this private attribute as the source of truth, so what the actual value of radius is going to be, and then we use the getter and the setter to control the access for it. So in this case, we define a setter for our radius. It takes in self and a value. What we do is we make sure the value is positive, and if it is, then we actually set the radius, which is our private attribute, to be that value. Otherwise, we raise a value error and we say that the radius must be positive. So now when I come down here and I say c.radius is equal to 10, what will happen since I've used this decorator is I'll go into this method and I'll start executing the code inside of here. So the value passed is going to be the value that I specified here, which is 10. We're going to do our check. Since it's positive, this will work, and we'll be able to set the radius. Now let's see what happens if we try to set this to say something like -1. Well, when I run my code here, notice we get an error, and it says the radius must be positive because our setter caught that this was a negative value, and it didn't allow us to actually make that change to the private attribute. So that's how the property decorator works. It allows you to control access to a private attribute and to have some logic be handled or called when you're getting or setting a value. Now, as well as getting and setting, we can also add a deleter method. So I've just slightly changed the example now to add the deleter method. Notice that the deleter method will be triggered whenever we use the del keyword. So if I go here and I run my code, we'll see that we get the output deleted. The reason we're getting that is because we first print deleted, we then delete the private attribute, and now we would no longer be able to access it. Now you can do anything you want inside of these methods, but the idea is you define one of them as a property. The name of the property is going to be the name of the method. Then you use whatever the method name is, .setter and .deleter, to actually write your own custom setter and deleter methods. You don't have to implement them. There's a few other options and things you can do here with properties, but that's the basic idea, and this is quite useful for creating read-only attributes, write-only attributes, or other custom behavior to really gate the access to the private attributes and control what's happening with the internal state of your class. So now we move on to a pretty popular decorator that you've probably seen before, which is static method. Now the static method decorator is used when we want to denote a method inside of the class as static. Now a static method simply means it's something that belongs to the class and not to an instance of the class, and it's not going to have any implicit first parameters like the self keyword or the class. All of that really means that we use the static method when we want to have some kind of function that belongs inside of a class but doesn't belong to a particular instance. So maybe we have some math class and we have a function like add or multiply. Now it wouldn't really make sense for this to be associated with an instance. We're not going to create an instance of this math class. We're really just using the math class to organize a few different functions so that they're in a logical area and we know where to access them. So this is a great example of where you would use a static method, and you need to decorate the method with the @staticmethod decorator. The reason you do that is so you no longer need to accept that implicit first parameter like self or CLS. Now in this case, the way that we would utilize these methods is by simply writing the name of the class. However, if you were to have an instance of the class, so we have something like m is equal to math, you can still call these methods using the instance. So I can say m.add 1, 2, that's perfectly fine, but what will happen since we've added this decorator is we'll no longer pass this instance as the first argument self, allowing us to just treat these as static methods. I don't have much more to say here, just always use the static method decorator when you need a static method. Moving on now, we have our class method decorator. Now again, like the static method decorator, this is used for a method inside of a class, and what this will do is transform the first implicit parameter or argument here to be the name or instance of the class, not an individual object. So typically when you call a method, right, you have that first parameter, which is self. So do something to define, get underscore name, self, and then maybe we'd return something like the name of this person. Now, when we use the class method decorator, rather than getting access to the instance in which this method was called on, we get access to the class, so person itself. Now, what that means is that we can only access attributes which are class attributes, like the one defined here, or other class or static methods. So we can pretty much only access anything that's defined on the class, not on the instance. So again, if we go here, we can print the value of CLS, and you'll notice that when I run my code here, we get the class main.person. We don't get an instance of the class, we get the class itself. That allows us to access something like a class attribute and to access other class methods or static methods. If this was a static method, we wouldn't get anything and we would not be able to access this class attribute. In summary, use a class method decorator when you want to access class attributes or other class or static methods, and use a static method decorator when the function is completely independent and it doesn't need to access anything else associated with the class or with the instance. Now moving on, we're looking at a decorator from the functools module, which actually has a few different decorators, and this one specifically allows us to cache the results of various function calls. This is super useful when you continually make the same call to a function, especially in a recursive case like the one I'm going to demonstrate here. So first, let me just break down an example where we actually need this, and then we'll look at how the decorator works. So here we have the Fibonacci function. This is a very famous problem in computer science, and the sequence that the Fibonacci function generates looks like this: 1, 1, 2, 3, 5, 8, etc. Now, if you haven't been able to catch on to the pattern, the way it works is the first two values are 1, and then the next value is equal to the previous two values summed together. So the basic idea is write some Fibonacci function where it gives you the value of n, so what the term n is equal to, and the way you calculate that is by simply calculating what the previous term is, and then what the second previous term is, and then adding those values together. Now, what this involves in this simple implementation is continually calling the same function multiple times with the same value, and the reason that's the case is because we get a recursive call stack that looks something like this. So here's an illustration of the recursive call stack when we call the Fibonacci function with the value 5. Keep in mind this is a recursive function, again, where we're calling n-1 and n-2. Now when we call the Fibonacci of 5, in order to calculate that, we need the Fibonacci of 4 and we need the Fibonacci of 3. Now in order to calculate the Fibonacci of 4, we're going to need to calculate the Fibonacci of 3 and the Fibonacci of 2. Now, in order to calculate the Fibonacci of 2, we need 1 and 0, and you get the idea. We're continually actually calculating the same values of Fibonacci exponentially more times as this value goes up. So what we can actually do instead here is cache the results that we've already calculated so that we don't need to keep calculating them when we already know what the result is. Now what this will do is drastically increase the speed of our function, and I'll show you an example of that right now. So just as a simple illustration here, I'm going to call the Fibonacci function here with a value of 40. Now you'll notice that I don't actually get an immediate result, and to be honest with you, I'm not sure how long this is going to take because this is a very, very poor time complexity algorithm, and we're going to run a lot of times continually doing the same computation that we've already calculated. So you can see here, even while I'm talking, it still isn't finished, and there you go, it just finished now. That took about 10 to 15 seconds, and I want to show you what happens now when we add a simple cache. So here's a modified version of the function now where we actually wrote in our own cache. This is us doing it customly, and you'll see that when I run the code now, we instantly get the result. Now let's see how we can do this in Python without having to actually modify the original function. So we've gone back to the original example, and what I can do now is I can simply decorate this with the functools.cache decorator. Now what this will do is actually write a custom cache for us, and it will automatically resize the cache so we don't need to handle that ourselves. So watch what happens now when I run the code. Same thing, we get the value instantly, and we didn't need to write our own custom cache. So whenever you're calling the same function repeatedly with the same arguments, you can cache that result using the functools.cache without writing your own custom cache. So now we are moving on to our final decorator, which in my opinion is the coolest one, and this one is the dataclass decorator. Now what the dataclass decorator will do is automatically fill in that boilerplate code that you're used to writing yourself. Now, in order to understand the benefit of it, let's look at the following class on our screen, and then I'll show you how the dataclass decorator works. It's also worth noting I made an entire video on this that goes through all of the details and intricacies. If you want to learn more, then check it out from the link in the description or the card on screen. Anyways, let's have a look at this class. So you can see here that what we're doing in this class is we're really just storing some information. So we might have a method, right, where we're calculating some cost, but generally we're just storing a name, price, and quantity, and then we're writing a representation method, something you've probably seen before, and we're writing a very basic equal method, so we can actually compare if two products are the same. Products are the same if they have the same name, price, and quantity. Now this is great, we can write this out, but Python has actually realized that this is a very common convention and people quite often do what you see here. So they've actually given us a shortcut to really avoid having to write all three of the methods you see here. Now that shortcut is using the dataclass decorator, so let's transform this code using that convention. So there we are, we now have code that is exactly equivalent to what you saw at the beginning of this section, where we now don't need to write the init, repr, or equal method. They're actually automatically implemented for us. Now, if you don't believe me, I'll show you a quick demo executing it, but the way this works is we import dataclass, this is the decorator, from the dataclasses module. We put this on top of our class, and what it will now do is it will read through the different attributes that we've written with their type annotation, so string, float, and int, and it will automatically populate the init, repr, and equal method for us. It can actually do quite a bit more, and it's very flexible in terms of how it works. Again, I made an entire video on it, but the idea is now all of that boilerplate code that we'd commonly have to write on our own will automatically be added for us. So let's paste in a simple usage example so you can see how it works. So I've just pasted in some simple usage here, and you can see that when I run my code, this works, and we get the results that were shown on the screen. The idea is our initialization is already written for us. Again, we didn't write that, but it's already implemented to handle the name, price, and quantity. We then have the representation method. So when we print out the product, we get it in a human readable form. We can call any of the original methods that were written on this class, and then we can use the equivalents to check if these products are the same. Notice that P1 and P2 were the same because they had the same value for each of their attributes. That is the data class decorator. Super cool. And with that said, that's going to wrap up this video. I hope you guys enjoyed. If you did, leave a like, subscribe, and I will see you in the next one.